Question number 11, it reads, a specially designed glass tube has a rectangular loop and only one opening through a tube extending from center of a longer arm of rectangular loop. This is the picture. So this is a rectangular loop and this is the opening which is in this liquid. It is filled with mercury and held with its plane vertical, and its opening is dipped in the mercury filled with a large vessel. There is some air in the middle of upper horizontal arm of the tube. So this is a upper arm and there's air, and that air is of twice L length, symmetrically L both sides. When the tube is stationary, ends of the air packet are at a distance L from the axis of symmetry of the tube. Pressure in the air packet is P and the density of the mercury is known to us as a rho. At what angular velocity must the tube be rotated about its vertical axis of symmetry so that pressure in the air packet becomes eta times of its value when the tube was stationary? So this is axis of symmetry, dotted line, and this is being rotated, if at all. So you'll find there's going to be change in the pressure. The question says pressure goes up from P to eta P. So what will be angular velocity for that purpose? So here's the solution. Let me explain how I have solved it. When air packet is at a distance r, so this is L, then if you start rotating, then you find centrifugal force is going to act on this mercury, and that will be pushing the boundary ahead. So when this length is going to change from L to another value, any general location, the distance is r from the axis of symmetry. Then the extra pressure due to rotation. So due to rotation, how much the pressure is going to come, that is going to push the mercury. So let's consider the dm mass of the mercury, and we know, and that dm mass which is at the boundary, you'll find dm r omega square. That will be the centrifugal force acting. So extra pressure is going to be this extra force coming in divided by area of the tube, cross-sectional area. Now dm is the mass of the mercury that we are pushing, so this is going to be density into the volume. Volume could be written as cross-sectional area into dr, because after r we are just considering dr element of the mercury, and into r omega square. Now A will cancel out, so this will lead to rho, the density of mercury, omega square, the angular velocity square, into r into dr. This is the extra pressure coming in, and that pressure is due to rotation, and that pressure will increase the pressure up to eta times of the original value. So we will be integrating this equation both sides. When you integrate, this omega square into density can be taken outside. It will be integration dp integration r dr. Now this will give us the change in the pressure. This is equal to r square by 2. That means final length. Let's final length becomes L prime. So it will be rho omega square L prime square by 2. So this is going to be the expression of pressure change when the distance changes up to L prime. Now this pressure change is given to us. So final pressure becomes eta P and initial pressure was P. So this will become equal to eta P minus P. From here, we can find out omega square. So omega square is going to be 2 times this expression divided by omega L prime square. So omega square is rho into L prime square. So omega square comes out to 2 eta minus 1 into P divided by rho into L prime square. So that's the angular velocity square. Now here P is known, eta is known, density is known. L prime, the final distance from the axis of symmetry, has to be calculated. Now assuming when this story is going on, pressure of the system does not change. This temperature of the system does not change. Pardon. So for this gas, we will be assuming this isothermal condition. Now if we consider these isothermal condition, then you'll find P1 V1 must be equal to P2 V2 for the gas in the upper tube. Now P1 is the initial pressure, which is P. V1 is the initial volume, which is going to be A cross-section area into the entire length, which is twice L, is equal to P2. Final pressure is eta P into volume, which is going to be A into twice L prime, because the final length is L prime from the axis of symmetry, right? So this gives us that L prime is equal to L by eta. So then L prime is going to be L by eta. Now since this came out to be L by eta, we can substitute over here. So omega square turn up as twice eta minus 1 into P divided by rho into L square by eta square. We can take this eta square upside and then take the square root to find omega. So omega turn out to be eta by L, because these are squares. So the square root bring them out as such. So eta by L within square root 2 eta minus 1 into P divided by density of mercury. So if you rotate with this angular velocity, then the pressure will become eta times the original pressure when the tube was stationary. So that will become a final response. Thank you.